Right, here's part 2 of our lecture on mod counters and clock division. So we want to understand clock frequency division and modulus counters that are not power of 2. Right, in part 1, we took a look at divided by 2, divided by 4, and divided by 8. And so this just refers back to the mod 2 counter that counts 2 clock pulses, 0 and 1, driving the creating a derived clock that's half the frequency or twice the period. Right. So we said it was really easy to construct those, right, due to the natural 2 to the n states of binary. But if we have a counter, say, that has a modulus value of 3, so if we wanted a mod 3 counter, that's not a power of 2. We want to have an idea of how do we design something like that. So we're going to call them mod M, where modulo M counters do not count all of their possible states, but instead count to the M value and then return to 0. The number M has to be a number smaller than 2n. So in the case of a mod 3 counter, we need 2 flip-flops are needed for the circuit, right? The binary count sequence is 0, 1, 2, right? Because we only, in a mod 3 counter, we only want to count 3 clock pulses. This is, right, we want to divide by 3. In order to divide by 3, we have to count 3 clock pulses. Then we need to roll back over to 0. So we skip the state 1, 1, right? We do need 2 flip-flops to represent then these sequences, but we skip the state 1, 1. So the circuit, right, the circuit is designed to force the binary counter to return to 0 partway through its count. Let's take a look at a modulo 5 counter. We want to count 5 clock pulses, right? Then we need to cycle back to 0 for a mod 5, which is also a divide by 5. So a modulus 5 counter, right? We're going, why does that say 3 clock pulses? We're going to count 5 clock pulses, cycling through the count sequence 0, 1, 2, 3, and 4, right? 5 pulses. Then we reset back to 0. The states 1, 0, 1, 1, 1, 0, and 1, 1, 1 are skipped. So here is our mod 5 counter state table. Here are our present states, right? We need 3 flip-flops, 1 for each bit. And so here in white on the left, these are the counts that we're going to sequence through. The states that we're skipping is in this sort of browny beige color at the bottom of this state table. We show the next states over on the right, right? So when we're on the first line, when we're in the present state of 0, so our count is 0, 0, 0, right? We said that our next count should be 0, 0, 1. So the next state is 0, 0, 1. When we're in a present state of 0, 0, 1, well, our next count, our next state should be 0, 1, 0. So you can see that each one of these states transitions from present to next at up counts by 1, except when we hit the last count, 1, 0, 0, we said at that point we need to cycle back to 0, 0, 0. All right, and here I've defined then these unused states. I've just said that the next state is going to be 0, 0, 0, right? That I want to go back to that state should we get any of these outputs. Another way, it's possible to treat these as don't cares as well. I just simply said I want to go back to state 0 in this case. Right. So we can use either a synchronous or an asynchronous counter. Right. Remember, all of the flip-flops in a synchronous counter are driven by the input reference clock. The asynchronous counter design uses the same ripple effect as some that we saw in part 1. And the asynchronous counter that we've seen in another lecture. Right. The first flip-flop clock input is driven by the reference clock. This is for asynchronous, while the clocks of the other flip-flops are driven by the flip-flop output in the adjoining least significant bit position. All right, let's take a look at what this looks like. All right, so down here I have the equations then for a D flip-flop. So next state equations, remember D is just going to be equal to Q plus. So D2 is going to represent Q2 plus, D1, Q1 plus, D0, Q0 plus. Right, so D2 is a function of, I don't know why I have that. O-ring there. And when I figure out why I put that there later, I may not be happy that I got rid of it. But D2, right, all of these then are functions of the present state, Q1, Q2, Q1, Q0, right? And so solving, if we go up here, notice we've only got 1, 1 in the output of Q2, and that happens to be for the binary 0, 1, 1, right, or min term 3. So we can say that D2 is equal to Q2 naught, and it with Q1 naught, and it with Q0, right? We then can derive equations for D1, which is going to turn out to be Q2 naught, and it with Q1, XORed with Q0. Same thing here, derive an equation for D0. We simply say that is Q2 naught, and it with Q0. And if we draw the circuit, right, if we solve it like this, we did something like this for our other state machine, right? And this a counter is a set of finite states, so it's a state machine, right, that only has clock input, no external inputs. All right, so except for, sorry, no external inputs other than reset and clock. Remember the reset, then we'll force our D flip-flops to produce an output of 0. We do have this reference clock, so this is this external clock input, right? If you take a look then on top, the flip-flop on top, right, is the Q2 output. You can see the output pin is labeled Q2. Right, we're generating the Q2 naught output. We've got our input logic of Q2 naught and with Q1 and with Q0 that was derived from this set of equations. Right, the flip-flop in the middle is D1, Q1, that generates the Q1 output. We've got that circuitry. Then our least significant bit in our count, right, is the Q0 on the bottom. There's that circuitry that we derived. And let's take a look at what happens if we then run this in the simulator. If we said, oh, this is a synchronous modulus 5 counter, will it really be a divide by 5 counter? So the functional simulation, right, produces this results labeled simulation 1 modulus 5 counter. The reset line is going to be held high just to show the counter results only. So you can see in the top line of the simulation resets high that entire time, right? Reminding you here that I used a Quartus D flip-flop, that it has an active low reset, so that's why the flip-flop has to be high so that it doesn't reset the output. Right. The second line of the simulation labeled input clock, right, has that that's the reference clock that's coming into the circuit. Then you can see in the middle, here's our reference count. So starting on the left, we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 3, 1, 0, 0. That's what we said we wanted to count, and we want to start back over at 0. So you can see at 25 nanoseconds, we do start back over at 0. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4 as you go across. That looks okay, right? If we're just grabbing that count, that looks okay. But we want to see if we have a divide by 5 clock. So what we're doing is we're going to start at 25 nanoseconds. A divide by 5 clock then should actually then end up using, right, we want 1/5 the frequency. So we should then count 5 clock pulses. So let's start here, right at the 25 nanosecond. There's 1 clock pulse, 2 clock pulse, 3, 4. And then on the 5th clock pulse, if you look at Q2, right, if Q2 is supposed to be our divide by 5 clock, Q2 is staying low for 4 clock pulses. So for that count of 0, 0, 0, 0, 1, 1, 2, and 3, it stays low, and then it transitions to high on 4, and it repeats this pattern, right, starting here at 25 nanoseconds. Right? If you look at Q1 at that clock, well, that clock is low for a count of 0 and count of 1. So for 2 clock pulses, that's low. And then it's high for 2 more clock pulses. So that is giving us a divide by 4. And then Q0 is actually low for 1 clock pulse, high for another. That is a divide by 2. All right. So we've got Q0 is a divide by 2, Q1 is a divide by 4. But for our divide by 5, we're actually getting 5 clock pulses where it's low for 4, high for 1 pulse. We want a 50% duty cycle, right? We want half of the time. So for half of those, or for 2.5 clock pulses, we want Q2 to be low, and for another 2.5, we want it to be high. We don't have that. So how do we get that? Right? And so the duty cycle of this is 20%. If you read down below, so the duty cycle is the amount of time in one complete cycle that the clock output is high. And so for 1 out of 5 pulses, this is high. 1 out of 5 is 20%. Right? Q1 produces a periodic signal with a duty cycle of 40%. So I missed that because over here, when I said this was a divide by 4, that was my mistake, because look, we have this abnormal behavior here. And we had it here to the left. I just missed that, where actually this is producing a clock that's low. So Q1's producing a clock that's low for 3 out of 5 pulses, high for 2 out of 5. That's a 40% duty cycle, right? Q1 produces then that 40% duty cycle, right? So like I said, dividing the input clock's frequency, the input clock's frequency by 5 requires that for every 5 input clock cycles, there be 1 output clock cycle. The output clock cycle needs to be low for 2.5 input clock cycles and high for 2.5. So this diagram here in the blue and the gray, where we're showing clock in, clock out, this clock out is the desired clocking signal, right? If we start on the left, you can see clock in, right, for a count of 0 is 1 period, count of 1, there's 2, count of 2, there's 2 clock pulses, and right in the middle of clock pulse number 2, our clock out signal transitions from low to high. It will stay high then for another 2.5 clock pulses, right, for the rest of number 2, for all of 3, and for all of 4. Starting over again at count number 5 here, right, at the 5th pulse, we would see this go low. That's the behavior that we want. So our new challenge, right, the output clock edge transitions on both positive and negative clock edges. Let's look at clock out here. Clock out, its first transition from low to high was where we go from gray to blue here on the left, right? At pulse number 2, when that clock in on that rising edge, that looks okay, rising edge. But when do we transition low? So we go across to the right from the blue to the gray. Well, the clock out transitions low on a falling clock edge. That tells us we're going to need a flip-flop that has a falling clock edge in order to drive this clock output low. Right. So to maintain a 50% duty cycle, we need 1 more flip-flop. What we do in general is we look for the waveform signal that's consecutively high for t-1 divided by 2 clock cycles over a period of t clock cycles. We delay this waveform by half of a clock period. This half clock period delay is achieved by adding another flip-flop of the opposite edge triggering. Right. So the frequency divided by 5 clock has a period of 5 cycles. So T refers to the period. So this formula here, T refers to the period, right? So divide by 5 clock cycles, number of cycles or number of periods, T equals 5. So if we follow that general formula of T minus 1 divided by 2, 5 minus 1 divided by 2 equals 2. What do we do with that 2? Well, we're going to look at the state values. We're going to notice that Q1 is high for 2 consecutive clock cycles and low for 3 consecutive clock cycles. We want to take a half cycle from the 3 low and add it to the 2 high of Q1. To accomplish this, we have to delay the output waveform of Q1 for half a clock period by adding another flip-flop Q3 to the circuit. Right. So this says, right, we look for the waveform signal that is consecutively high for t minus 1 divided by 2 clock cycles. We said that our t was 5. 5 minus 1 is 4. 4 divided by 2. So that's why we're looking for a waveform signal that's consecutively high for 2 clock cycles over a period of 5. So out of a period of 5, Q1 is high consecutive. See this 1 and 1 together? That's consecutive period. Here's a total of 5. So that's what we mean by consecutive. You could see that as well if you go back. Then right to the functional simulation and look at Q1 signal, you can see out of those 5 pulses, it's high for 2 consecutive. It's low for 3 consecutive. So we look for this consecutive high of 2. Right. And so we're going to add flip-flop Q3. And why is that significant for Q1? Right. So we say, assuming that Q2, Q1, and Q0 are all positive edge trigger flip-flops, they were in our circuit, Q3 must be a negative edge trigger, right? It needs to be the opposite. What we're going to do then is we're going to take the output of Q1 and we're going to make that the input of Q3. We're also, in order to make the Quartus flip-flop a negative edge triggered, we take the clock signal and we invert that, right? It's a rising edge, positive edge clock triggered. If we invert the clock signal, we'll end up with a falling edge or negative edge clock signal, or triggered flip-flop, negative edge triggered. Right. So our divide by 5, our modulus counter then looks like this. We've changed it. Right, we've added, so we kept Q2, we kept Q1, and we kept Q0. So that work we did before didn't go to waste. We added on top a Q3. That flip-flop then, the input to that is Q1, right? And we've got the inverted clock to make that negative edge triggered. We said that needed to be negative edge triggered. Right. And now, right, what we're going to do is we're going to take a look at the functional simulation, right? So it's going to illustrate the output of Q1 and Q3. What we're going to see here, right, our reset's held high, so we never reset. You can see clock then is oscillating, right, at the reference clock, Q1. Well, let's take a look at what Q1 does over a period of 1. So starting here at 10 nanoseconds, that line in blue, got 1 cycle, 2 cycles. So for 2 clock pulses, right, Q1 is high. For 1, 2, 3 clock pulses, Q1 is low. Let's look at Q3 during that time. During that time, right, and we're going to look at the negative clock edge, right? On that negative clock edge, which is about 12.5 nanoseconds, right, we've got Q3 rising. So 5 clock pulses, Q3's high for 2, low for 3. But notice it's shifted over by half a clock period because we have that negative edge on Q3. Our final step then, right, and so this says, right, that each one of these have a 40% duty cycle. Our final step is we're going to add an OR gate to the circuit to provide the divide by 5 output. We're going to combine the Q1 and the Q3 outputs. We're going to OR them together. Right, so we OR Q1 and Q3 together to generate then that divide by 5. And so now if we run a functional simulation, and so here shown in blue in the functional simulation, this is the divide by 5 output. We're showing the outputs of all of the flip-flops, Q2, Q1, Q0, but simply by ORing Q1 and Q3, well, we know, right, Q1 was the one that we took a look at that we wanted to adjust, right? We said we needed to adjust that one by adding a flip-flop Q3, making it the opposite edge triggered of Q1, inputting Q1 into that flip-flop, right? Didn't produce our divide by 5 until we said, let's OR these two together, because when we OR these two together, let's take a look at Q1 from 10 nanoseconds to 12.5 nanoseconds, Q1 is a 1, right? If we OR that with Q3 that's a 0, we know our output's going to be a 1. Same way here, because we've shifted Q3 over by half a clock period, when we OR that, then at about, let's see, at 20 nanoseconds, when Q1 is low and Q3 is high, when we OR that together, that produces a 1. So what we're going to do is we're going to produce a 1 from 10 to 20 nanoseconds, from 20 to 30, we're going to produce a low because both Q1 and Q3 are low during those time periods. We'll end up then getting a 0 out of that, right? That's why we chose to OR them together, right? So you can take a look, like we said, where our count was correct before. Our count that we grabbed, we have our separate count output. We're still grabbing that in case we want to read this count. But to get the divide by 5 clock, right, we added in this extra output, which is the result of ORing Q1 and Q3 together. So this then divide by 5 is the clock we were striving for. Like I said, if for some reason you wanted to read these counters, you could grab this output and this count output out of the flip-flops. Right, so that's how we do a divide by 5. And we do the same methodology to create other modulus counters that aren't powers of 3. Right, you could take a look at, go back and try a divide by 3. That's a little bit, it's the same methodology. It might be a little bit simpler simply because there's less flip-flops in the original equations. Right, so anytime that they're not powers of 2, we have to follow this methodology. Right. Now, what this is also telling us is that we can cascade, right? In the other lecture, we saw that we could cascade divide by 2s together, right, to get divide by 4s and divide by 8s. Well, we can cascade any counter together. So when we cascade them together, what that means is, notice here we've got a divide by 2 and a divide by 5. So if we take this divide by 5 circuit, make a block symbol out of it, right? Here on the left, I've got a divide by 2. Here's our reference clock input into the divide by 2, right? We've got a reset attached to both of these. What comes out of the divide by 2 circuit and feeds into the input of the divide by 5 is the divide by 2 counter, right? But that feeds into the clock here. What will come out of the divide by 5 then is a divide by 10. Notice the output pin is named divide by 10. So if you take a number divided by 2, and then divide it by 5, you have effectively divided by 10. You can make a block symbol out of this to create a divide by 10. So you don't have to then create a separate circuit for divide by 10 and go through the truth table, right, and find out where do I have to add extra flip-flops to adjust for that. In this particular case, since we have the divide by 5 and the divide by 2, we're not going to make a divide by 10. We could make a divide by 25 by cascading 2 divide by 5s together. We could cascade 3 divided by 5s together to get a divide by 125. You could cascade a divide by 2, and divide by 5 to get a divide by 20, or divide by 2 times a divide by 10. Right. So cascading the clocks together that allows us to create a lot of other clocks that are obviously multiples of these. We couldn't create a divide by 7. We'd have to go back to this methodology that we saw up above to come up with a divide by 7. Because 7 is not evenly divisible by any multiples other than 1. And 7, it's a prime number, so we'd have to create a clock if we needed to divide by 7 for that. Right. And so here's a simulation as well of the divide by 10 circuit, down here labeled simulation 4, right? We're not resetting this. It's held high the entire time. You've got your reference clock input in the middle, your divide by 10. Well, if you look at, if we start counting here at 12.5 nanoseconds where the blue line is, if you count, you can see then that for 5 clock pulses, your divide by 10 is high. For the next 5 clock pulses, your divide by 10 is low. So 1 divide by 10 is 10 clock pulses, right? All right, so that's it then for dividing by non-powers of 2, this part 2 lecture. Is it go out, create these circuits, simulate them for yourself, see how they work. Go ahead and try a divide by 3.